Good afternoon. My name is Luis Luro. I'm part of the group project of the Dynamometer. Uh, and today I'm going to present Phase B of my subsystem, which is the system for emergency brake system. The agenda for today is the trace studies for my subsystem, which will include three different types of emergency brake systems, my architecture into components, the rating weighting for the critical components of my subsystem, the risk assessment, the safety factor identification, and the project planning. Emergency brake selection. The trade studies, as you can see, there are three types. The one is the water brake system, which includes water stored in the tank, which will be pumped into the rotor that will start that will push the rotor and that will stop the dyno, and then after its use the water will be pumped back into the tank for another use. The spring brake system, this one has compressed air that will fill the chamber or that will fill or release from the chamber by pushing the push rod, and this will what this will do is compress the spring each time the brake is in use until the dyno stopped. Once stopped, the spring will release and return to its relaxed form. The third system that we will use to compare is the disc brake system. This one is we see in every day, which because it is in the cars. This is in a hydraulic system which pushes the oil all the way to the piston. The piston will push the brake pads, and they will close onto the rotor until stopped. Here we can compare each system, the water brake system, the spring brake system, and the disc brake system, using the different MOPs chosen for my subsystem. The most important ones are the cost. The water brake is $9,000, which is a lot. It is actually more than the budget allowed, but for the university for the whole project. The spring brake is $1,000, and the disc brake is around $550. Excuse me. Uh, Another important one is that the dyno has to stop in 2 seconds or less. All three of them they do that, and the number of components. Less components, less money that we have to use, and less risk that there will be in when the subsystem is in use. With taking into consideration these MOPs, I did the rating weight decisions to make a decision to see which subsystem I'm going to use. As I previously said, the cost is the most important. The low number of components is the third important, and the dyno should stop in 2 seconds or less is the second most important for this subsystem. After doing the rating weighting, it is determined that the disc brake system is the most suited for the design. Now my hierarchy diagram, as you can see, at the top at tier 0 we have the group project, that is the dynamometer. That is divided in 4 subsystems, which is my the tier 1 roller, chassis, brake system. Those will be explained by my teammates. And the emergency brake system, which is my subsystem. It divides into more subsystems, which is my tier 2. We have the mechanical system and the hydraulic system. My mechanical system divides into components, that is the brake lever and the disc rotor. I will be explaining these. And the hydraulic system divides in 4 components, that is the master cylinder, the caliper, the brake pad, and the hydraulic line. Most people could say that the caliper is another subsystem, but since it is actually with the param after I do my calculations, I choose those criterias and I can buy a caliper already done. I don't have to do it from scratch. That's why it's a component. My interface, a dynamometer which is ours, is going to use a roller with a diameter of 14 inches and has a mass rotation of 15,000 RPM. The brake system, as I said earlier, will be a disc brake system, and I have to determine the diameter of the disc rotor to be used. It can't exceed 14 inches. The force needed to stop the roller in 2 seconds or less. That is really important. That way I will choose the brake pads, the caliper, and the master cylinder required for that force and the line of action. Now will explain the components of the hydraulic system. First, for the caliper selection, there are two types. One is the floating caliper, which basically has one piston, and when the fluid goes in and presses the piston, it presses only one side of the rotor. This will this will make the rotor wear unevenly since it's only pressing one side. And the other type we have is the Fitz caliper. This will actually use two, four, or six pistons. That way, it will since it is both sides, it actuates on both sides of the disc. It will it will provide a more even wear for the disc rotor. The wear now in my rating weighting, I have the criteria is spacing, the braking power, the number of pistons used, because with this number of pistons used, the more pistons used, more braking power. The cost, which is always a factor in all our rating weights, and the wear of the disc. The wear of the disc is important because if it wears uneven, just as the floating caliper does, it will start making noises. It will start moving weird, and that is something we don't want. It will start break it, which will create because it will create problems on other components and maybe other subsystems such as the roll and the chassis. After doing my rating weighting, I chose the Fitz caliper to be the most suited for my design. Most likely because of the it has more braking power and it's in in the wear of the disc. Now for to select my master cylinder. There are two types: the tandem master cylinder and the single master cylinder. The difference is in the tandem master cylinder we have two we have two springs actuating and two reservoir tanks. This is and when we compare it to the single master cylinder, it only has one spring and one tank. The number of tanks is important because if, by example, the tank breaks, well, if it's in the single master cylinder, if the tank is broke and it has a leakage, you won't be able to stop the dyno. Meanwhile, in the tandem cylinder, if only one of them breaks, then you can still stop the dyno because you will have another tank. Maybe not with the same force, but you'll still be able to stop it. Now, using my rating weight decision, my criteria were number of pistons. No, it has to be normally closed when the dyno is not in use, which means it has to be stopped. If someone that doesn't know how to use it tries to use it, they won't be able to activate nothing because it will be stopped. The roller will be stopped. Safety leakage occurs, like I explained earlier. Uh, this is just in case the oil tank breaks. And the cost. The most important one is the safety because that's like the motto, the important part of the emergency brake. There has to be it's safety. So if it leaks, you won't be able to use it, and we want this subsystem to be used whenever it's needed. It has to be ready for whenever it's going to be used. After doing the research and putting the weights, I determined that the tandem master cylinders is the most equipped. Um, most like mostly because of the safety, like I said. Now the brake for the selection of my brake pad, we have organic brake pads, semi-metallic brake pads, and the ceramic brake pads. The difference between all three is the material. And the material of each will determine my criteria, which are temperature, fade resistant, operating function, pad life, and cost. After doing the research, the temperature fading, the organic pad is the best. The operating function, the ceramic pad is the best, and the pad life, the two best are semi-metallic and ceramic. The most important part in these is the cost, and then is the temperature fade resistant because we don't want the subsystem to overheat. And after doing the research and everything, I chose the ceramic pad. Now, for my mechanic subsystem, I will now present you the trade studies of the two components. One is the emergency brake actuator. I have two. The emergency, I have an emergency stop push button. This is commonly used in most machines in the industry. You press the button and it will automatically stop. It is, I chose it as mechanical because you still have to press it, but it is most likely electrical. We also have the emergency brake drifting lever. This is most used for enthusiasts of brake drifting. It is easier for them than using a normal car e-brake lever. Um, my criteria. I, I will have to be able to use any of these actuators in any circumstance. I have to be able to use it if there's no water, no air, no electricity. Normally closed when not in use. That both of them have that requirement. The time response, which is how much time does the signal take to travel from the actuator to my subsystem, which is the caliper. Calipers, first the master cylinder, then the caliper, then the brake pads. And the cost is pretty important. The time response is pretty important. The emergency stop will win in that category, but that is only if there is electricity. Excuse me. If there is no electricity, it won't work. After doing the rating weighting, I chose that the drifting emergency brake is the best suited for my design. The last component of the mechanical subsystem is my disc rotor. We have three disc rotors: drilled, slotted, and smooth. The difference is, as you can see, it's aesthetic. You can see the differences. The drill has holes, the slotted has some lines, both of them patterns, and the smooth one is the normally used for cars. The criteria I used is fast natural cooling rate. It has to cool down fast. The faster the better. That way we prevent overheat and we can use it faster. The disc wear, I said earlier, the disc wear is due to if it's even. The hot it has to be able to stop at a high speed without breaking any other components. Uh, the grip it will have with the pads is important, and the cost. After doing the rating weighting, I chose that the slotted disc rotor is the best suited. Now my risk assessment includes for both subsystems, the mechanical and the hydraulic. First, the subsystem doesn't shut down in 2 seconds or less. That's a risk that we have to take into consideration. The mitigation strategy should be to inspect the subsystem before every use. And in the other table, you can see the probability percentage and the impact. For this, it will have a low probability. This won't happen much, and the impact is it's low, but it's borderline medium, because if we aren't able to stop in less than 2 seconds, then it will only be a normal break. It won't be an emergency break. My second risk is that the lever will break when used. Um, this For this, the mitigation strategy will be I have to choose a lever that will hold up more force than the max force that can be applied by a human, by an average human. This it will basically never happen. It could, but most likely won't. That's why it has a low impact and low probability. My third risk, the project will slide off the dyno. For this, my mitigation strategy is that the operator shall double check that the project is well tied up. If I apply the emergency brake, the project cannot slide out the dyno. Um, it is a low probability. It could happen because we are human and we make mistakes. It will be a medium, it will be a high impact, because not because the subsystem will break or anything, but it's because of the safety. If the project slides off, the project may most likely will break, and if there's people close to the dyno, they will get hurt. The next risk, the dyno or the project will break. The mitigation strategy is that the theory that and formulations that I will make, I'll it will be tested just to make sure that the subsystem cannot stop. Can excuse me, that the subsystem can stop the roller efficiently. If this occurred, if the dyno would should break, it will have a medium impact. It's a low probability, but it's borderline high impact, because if the dyno breaks, then we have to fix it. That will include cost, the safety of the people using it. The same with the project. The project could harm people, and most likely the project is on a time restraint, so it will affect the people of the project. My last risk is the overheating of the subsystem. My mitigation strategy is that the design will include this this risk, and I will choose the components accordingly. As previously seen today, and for the components chosen, I took that into consideration for my brake pads, which is important. They cannot overheat. It's This risk is a low probability because the design already includes this fact. But if it did overheat, it will be a high impact because it won't be able to to stop the dyno efficiently. Now more for my safety factor identification. The formula is safety factor is equal to the safety factor of the material times the safety factor of the failure analysis times the safety factor of the geometry times the safety factor of reliability. As you can see on the table, I chose there is the factors, each factor, which is material load stress, failure analysis, geometry, reliability, the description of the safety factor that I chose, and the number, the value. For this, after doing the calculation, the safety factor I should use for every calculation that I made should be 3.432. This is my subsystem timeline for phase C1. It is divided by weeks from October to November, since my presentation date is for November 14, 2019. Thank you for your attention. Luis Luro was speaking. Please have a nice day.